Assalamu alaikum and very good evening to my dear audience. This is my initial seminar presentation of PhD research entitled as Development of Optimized Deep Segmentation Framework for Diagnosis of Pneumonia through X-ray Imaging. These are the contents for my presentation. Introduction. Pneumonia is a lung disease that makes breathing difficult and painful, typically caused by viral, bacterial, or fungal infections. Each year, 450 million people are affected by pneumonia, ranging from mild to life threatening. Therefore, it is necessary to diagnose as early as possible. And with AI powered algorithms, diagnosis becomes more faster, more accurate, and cost effective. Especially in the low resource settings where patients are waiting in outdoor emergencies and doctors are limited with variability in the expertise and probability of human errors. Therefore, automating pneumonia detection is the goal. Every 13 seconds, one person dies from pneumonia. This graphic highlights the pneumonia's global impact. In 2019, the disease caused 2.5 million deaths, with the highest risk observed among children under 5 and elders among elders more than 70 years. Pneumonia detection using chest x-rays. Chest x-rays are the primary diagnostic tool for pneumonia. X-rays are less expensive and more accessible than CT and MRI scans, making them ideal for this study. However, analyzing chest x-rays is challenging due to the subtle differences between the healthy and the infected lung tissues. Automated detection, pixel level segmentation on X rays. Traditional pneumonia diagnosis relies heavily on medical experts, making it time consuming and subjective. Automated pixel level segmentation is a powerful computer vision approach that categorizes every pixel into a specific class. This is the sample of pneumonia detection and the pneumonia segmentation. In pneumonia detection, there is the bounding box that contains unnecessary information as well. In pneumonia segmentation, there is a boundary based box that contains the precise delineation. Deep learning in medical imaging. Deep learning models like convolutional neural networks have revolutionized medical imaging, and they help in identifying complex patterns in X-rays. This is a sample image of pixel segmentation task via a deep learning model performing pneumonia detection on the chest X-ray image with the help of encoder and a decoder architecture that extracts meaningful features from the input image and reconstructs the output segmented image while preserving the spatial information. So the research scope is that the focus of this research is on the pneumonia detection using the publicly available data sets, and the data modality is the image based, and the task type is semantic segmentation, a level ahead of the normal segmentation. The model type is convolutional neural networks that are best suited for image processing and the medical imaging. The limitation is that we are only considering the X-rays, not the other modalities like X-rays, like CT or MRI scans, and also we are not considering the other lung conditions except the pneumonia. This is the literature review. In the literature, most of the work deals with the detection and the classification. There is very limited research on the segmentation. In the first, let's say the first researcher, Osterg, with the citation number 27, it developed an automated model for the pneumonia detection on the chest X-ray images. It emphasized the detection of on the classification task, not on the segmentation task. The second researcher with the citation number 28 used the transfer learning models, and it also focuses on the classification accuracy rather than the segmentation of the pneumonia. The Paul Molly with this edition number 26 worked on the class imbalance problem. Then it observed that using the data centric techniques, it also helps in the pneumonia segmentation problem. The another researcher Raghu with the citation number 29 worked on the data pre-processing techniques, and it was observed that using the data pre-processing techniques, the pneumonia segmentation model enhanced and gives the more better results. These are some papers on that are specified to this research. The first paper is that on the with the title segmentation performance analysis of transfer learning models on X-rays pneumonia images. In this paper, the authors have used three different models like UNIT, SegNet, DeepLab V3, and they compare the performance of these three models, and it is observed that DeepLab 3 outperformed than the other two models. And they worked on the dataset of the Women and the Children Medical Center. And this is another paper on with the title Pneumonia Transfer Learning Deep Learning Model from Segmented X-ray Images. They all worked on the transfer learning models from ImageNet and the SQSNet, and worked on the BoxCNet model, and they improved their results. And it was observed that with the segmentation, the accuracy they get, it's about 98.6%, and without segmentation, the accuracy is 97.6%. And this is another paper, automatic lung segmentation in chest X-rays using images using dilated dense RAS unit. And they also worked on development and the evaluation of lung segmentation model, and they worked on the modified UNet architecture. And this is another paper on the title a comprehensive segmentation of chest x-rays improves deep learning based World Health Organization radiologically confirmed pneumonia diagnosis in children. And they also observed the dice coefficient similarity of 96% and with a good ratio. And there are some other papers that are cited in this literature, with the paper title Objective Methods, Key Findings and the Limitations. So there are still the challenges in the pneumonia segmentation, like the complexity of the task and the data limitations. So the literature review summary is that pneumonia segmentation remains complex due to challenges in precise delineation. Most research focuses on detection and classification, leaving segmentation underexplored. A major issue is the lack of properly labeled datasets for the segmentation, and the poor data processing affects the model performance. So to overcome these challenges is the aim of this research. And problem validation through experiments. To validate the literature, some initial experiments were conducted on the publicly available dataset. The first experiment belonged to the impact of data-centric techniques on pneumonia detection. That deals that what happens when we are using the data-centric techniques and what happens when we are not using the data-centric techniques. And the second experiment deals with the performance evaluation of the existing segmentation model. And the third experiment that belongs from the experiment number 2, that with the usage of segmentation model, how much that model detect or identify the pneumonia region that's infected. The dataset used in the experiments is taken from the RoboFlow, and it consists of 4,745 annotations for the binary classification, distinguishing between pneumonia positive and the pneumonia negative cases. These are the sample images of the dataset. This green contains the healthy lung, it means pneumonia negative, and this red lung contains the pneumonia positive. This is a class-wise distribution of the dataset. That out of 4,745 total images, 2,405 are the pneumonia positive samples and 2,340 are the pneumonia negative samples. And this dataset is split into the trend set, validation set and the testing set. The training set is almost 56%, the validation set is almost 26%, and testing set is almost 18%. This is the pixel-wise distribution of the dataset. The left plot shows the total pixel count of all the images per class of pneumonia positive and the pneumonia negative. And the left plot shows the distribution of the pixel count per image with the stack bar showing the portion of the pneumonia positive and the pneumonia negative. This is the methodology of the experiments, that the data contains the original image, the mask image and the annotations, and this data is then feed into the network of the convolution neural networks. Here we have used the UNet architecture that is most popularly in the segmentation task, and the output of these segmentation model is that the evaluation metrics we consider is about accuracy, precision, recall, intersection over union and the dice coefficient, and the output we are getting the segmented image. Model setting and the parameters. The input image we giving to the model is the uh, original image, that is an RGB format, 3 channel, and the segmentation mask, that is 1 channel image, the black and white image. The model we have used is the convolutional neural networks, and the comparison we are running in different CNN layers, like max pooling, dense layer, flattened layer, optimizers, random optimizer, atom optimizer, different activation functions, and the loss functions. The training we train the data, we train this model and the data set on the 25 epochs, but put the condition of the RD stopping. That's why the model is stopped on the condition of the 5 to 10 epochs. The batch size is 32, learning rate is 0.01%, dropout is 0.25 to 0.35. The evaluation metrics is the pixel wise accuracy, precision, recall, dice coefficient, and the intersection over union. And the first experiment deals with the impact of data-centric techniques on pneumonia detection. The data-centric techniques basically focuses on improvement of the data quality by working with the data pre-processing and the data augmentation techniques. So initially we deliberately omitted the data pre-processing and augmentation and the class imbalancing techniques to assess the baseline model performance, and it was observed that without using these techniques the model degraded the performance, and with usage of these techniques the model gives better results. This is the algorithm for this experiment, and this is the confusion matrix of the classification results of this experiment. Is that the true negative, true positive, and the false positive, false negatives are there. And here you can see the change in there are false negative is 50 before, and after the false negatives are reduced to 11. So significant reduction in the is very critical in the healthcare. Let's say if there are positive samples of the pneumonia, but the model say no, there is no pneumonia, there is a negative. So this will generate the consequences. The experiment one results is that before pre-processing, before working on the data-centric techniques, the results were accuracy is 69%, and after applying that working with the data-centric techniques, the result accuracy is 85%. Precision before is 63%, and after the precision is 82%, and so on. This is the training loss and the training accuracy curves of this experiment. The training loss curve, that the red dash line shows the before training loss, that is higher. That means that the predictions were further from the actual values. The after training loss is bit lower. That shows the model is now a model has learned to make the better predictions. The training loss is basically the measure of the error between the predicted and the actual outputs, and the training accuracy is basically the measure of the percentage of the correctly identified samples during the training process. So the after training accuracy, you can see it's increased, and before the training accuracy has been degraded. And this is the ROC curve of this experiment. ROC curve basically distinguishes between that how well a model distinguishes between the two classes, that's pneumonia positive and the pneumonia negative. And in the after data pre-processing techniques, you see the accuracy is 85%, and before it says 65%. This is the second experiment for that. About these working on the segmentation model, assessing the segmentation model, that how well they generally do perform. So this is the algorithm for second experiment, and these are the results for the second experiment. Is that the dice coefficient is 62%, intersection over unit 55%, precision 68%, and recall is 59%. So these results are not that much up to the mark. Problem validation through experiments is again the experiment number 3, inaccurate region of interest detection. This is generated from the experiment number 2, that shows the how well that model precisely detect the pneumonia region. So this algorithm for that, and this is the results, and this shows that some classified and the misclassified samples, and these are 4 categories. This trained on the two classes, that's pneumonia positive and the pneumonia negative. The multiple different colors are showing the confidence level due to the heat maps about the variations in the intensities of the pneumonia detection regions. So the bottom line of experiments is that the experiments confirm that the pneumonia segmentation is still an open problem due to inadequate pre-processing and data limitations. Even with pre-processing, results were suboptimal. So even though the results were suboptimal, so it reinforces the need for the optimized deep learning framework for pneumonia diagnosis with improved data handling and um, evaluation. So there's a focus of our research. The problem statement is that traditional pneumonia diagnosis relies heavily on medical experts, and traditional pneumonia diagnosis methods are subjective and prone to errors. Despite advancement in medical imaging, um, accurate segmentation is still underexplored, limiting the diagnostic precision. So this research proposes developing an automated framework for pneumonia detection to optimize the accuracy and the efficiency. This research is guided by 4 questions, and the first research question is that what data-centric techniques can effectively address the data challenges encountered in medical imaging. The second research question deals with which features are essential for the accurate pneumonia disease detection, particularly at the pixel level in chest images. The third research question deals with the how can we develop and optimize a model leveraging the identified features to enhance the accuracy of pneumonia detection, disease detection. The fourth research question deals with the which validation techniques are suitable for evaluating the performance and robustness of the proposed optimized model for pneumonia disease detection. The research aim is that to develop and optimize deep learning based framework for pneumonia segmentation through X-ray imaging, and to achieve this aim, the following objectives are there. The first research objective is that to utilize data-centric techniques to address data-related challenges in medical imaging. The second research objective is that to utilize and prioritize features crucial for pixel level pneumonia detection in chest images. The third research objective is that to develop and optimize a model using the identified features to enhance pneumonia disease detection accuracy. And the fourth research objective is that to evaluate the performance of model on benchmark datasets and compare its effectiveness with the state-of-the-art models. This is the research contribution with respect to the, it's mapped with the corresponding research question and the research objectives. The first with the research contribution that deals with the research objective as a question of the utilizing the data-centric techniques is that we can conduct the in-depth literature review and identify the best practices and proposing new techniques for that. For example, we can also propose the novel loss functions for the class imbalance problem, let's say. The second research contribution for the second research question and the objective is that we can identify and prioritize the key features that are crucial for the model development and investigate the feature extraction methods that are utilized and that can be customized as well. And the research contribution third is that development of an optimized model for the third research question and the third research objective. The fourth research contribution for the fourth research question and research objective is that we can work on the enhancing the clinical applicability, that how well the implementation can be best fitted into the clinical laboratories, and advancing research standards, comparing and validating the benchmark datasets and the state-of-the-art models. This is the action plan for the research that conduct a literature review, identify the research gap, data acquisition, data pre-processing, feature selection, model development, model evaluation, model validation, results analysis, and the documentation and the reporting. This is the proposed research methodology of this work, that first we work on the data acquisition, that we selected the data set that's publicly available, and if the annotations are not there, we can also work on the annotations and the data verification part if needed. And the data is in the format of the original image, mask image, and the annotated image that contains the annotations for that. And this input data is then data pre-processing and augmentation techniques are applied on that, like data cleaning, data normalization, handling the imbalanced problem conditions. And after the data pre-processing and augmentation, there is a feature selection method for that, and like different feature extractions and the dimensional reductions, that which features are crucial for the model development, and different methods are there. We can like work on proposing different novel methods for that, like ablation studies removing specific features and observe the performance drop helps in identifying the critical features. And the model development, we can work model optimization, model evaluation. Different performance metrics are there, like accuracy, precision, recall, and the segmentation metrics like dice coefficient, intersection over union. And the output, we get the segmented image. This is a list of data sets that we can utilize. There is available list of publicly available data sets on the Kaggle, RoboFlow, and other sources with the variations in the sample size, and some limited data limitations are there, that some do not contain the annotations, some have access problem, requesting the access, some have size problem, and some have class imbalance problem, and many other reasons for that. Some have diversity of the data. So there are different challenges in the data set. We will see which data set we are going through with our research. These are the evaluation metrics that we can work on: accuracy, precision, recall, dice score, and the intersection over union. Dice score, coefficient, and intersection over union are for the segmentation task. Dice similarity coefficients is basically the measure of the overlap of the actual and the predicted output. And intersection over union is basically the ratio of the predicted and the actual segmented output over the union. These experiments and setup contains the hardware and software and the internet connectivity and the Python Anaconda. Um, Python Anaconda software or the online repositories are there, like Google Colab, Kaggle Notebook we can also use for that. And then the way forward is that the next steps ahead, the refining the model, we can work on the multi-model data, we can work on the synthetic data generation like generative AI in the data acquisition part, and then the collaboration with the healthcare institutions, scalability, and the real world deployment. We can also work on the explainable AI, that how that deep learning model made certain decisions, to understand that interpretability and the transparency. We can use that explainable AI. And the continued research publications, and this is tentative research timeline for my research. Currently I'm on the initial seminar stage, that March 2025, and this is the tentative time schedule for that. And these are the references that include the peer-reviewed journals, data sets, and the benchmark studies relevant to my research. So also one few questions that I would like to discuss about the dataset. One question can be arise regarding dataset is that why I'm utilizing the publicly available dataset, why not the connecting the real world data? It's because utilizing publicly available dataset allows me to focus on developing and optimizing the deep learning model without the complexities and the time constraints associated with real-time data collection. Real-time data collection from hospitals involves challenges such as patient privacy, ethical approvals, and radiologist validations, which are time consuming and resource intensive. And additionally, standardized data sets provide a benchmark for comparing my model's performance with existing approaches, ensuring the validity and the reliability of the results. And the next what else we can discuss, it's about, yes, we can also discuss about the I have repeatedly told about the traditional pneumonia detection methods. So what exactly are the traditional pneumonia methods is that traditional methods can be the clinical examination, like assessing the symptoms like cough, flu, chest pain, fever, and listening the lung sounds using the stethoscope, and observing the chest X-ray, CT scans manually, and seeing the lab tests like blood tests, oxygen levels. So these are the traditional methods. And here we discussed about the in literature we discussed about the class imbalance problem. So class imbalance problem can be tackled with using different techniques like SMOT, oversampling the minority class and undersampling the majority class, and the class weighted sampling and the different loss function adjustment. We can balance the data. And one thing more I would like to discuss regarding the yes. So the X-rays are the deep learning models requires the grayscale images. Here I have mentioned that are three channel image, that's the RGB, but the model the deep learning models requires a grayscale image. So the question can be arise that X-rays are already black and white or the grayscale image. Why we need the conversion? No, the X-rays are inherently grayscale, but when saved as image, they are stored in the RGB format. And the RGB format is what? Each pixel contains three channels, and red, green, and blue. And the grayscale images are the single channel images that each pixel can contain the intensity from black 0 to white, that's 255. And another thing I would like to discuss about the mask image again from here. Yes, I have generated this mask image myself, so we can generate this mask image using different automated tools like MDAI, Label Me, and there are so many other online tools available for that. But we can also work with it with Python. That I have used the OpenCV IM read function, and then to load the data, and then converting this image into the zeros for the background, and using the function of numpy zeros function to make this image as the black and the zero. And then the corresponding annotations, the coordinates of that annotations are masked with over this with the one white over this black. So the coordinates or the annotations are replaced with the white color over this black image, and then this image is then converted into this black and white image is then converted into the grayscale by using the from array function of the Python image library. Then it's like mask multiplied by 255. And also I would like to tell about the distribution of that. So this pixel calculation or pixel wise distribution, how I have calculated this is like using this segmentation mask that I have explained earlier. That's the black and white image, and so the black is the background and the white is the foreground. And so using that segmentation mask where each pixel labeled as pneumonia positive as 1 and pneumonia negative as 0, using the numpy sum function, we can count the pixels belonging to each class. So this process is repeated for every image to calculate the per image pixel distribution. It's like that. And also the pixel wise segmentation models can be the SAM segment anything model, detectron 2 unit model, and mask RCNN, faster RCNN, deep lab. There are many other different pixel wise segmentation models are there, but we will see which we are going with. And also another question can be arise with from yes here, that why we are using the machine learning model, why we are not using the machine learning model, why we are using deep learning model, and why we are using the convolutional neural networks, and why we are using the convolutional neural networks, why not the other latest technologies like vision transformers and the attention mechanisms. So the first question is that why we are not using machine learning is that it requires the manual feature engineering, it struggles with the spatial dependencies, and that's less effective for the pixel wise segmentation. So that's why we are using the deep learning, because it enables automatic feature extraction, pattern recognition, and end-to-end learning, making it more suitable for pixel wise task. And why we are using the convolutional neural networks, because they are well suited for the medical imaging. And why we are not using the VLMs, vision language models, or the attention mechanisms, or the transformers, because they requires large data sets and extensive training, while the convolutional neural networks are computationally efficient and effective for medical image segmentation. So these are all the this was all about my presentation, and I have also justified few of the questions that were on my mind. So thank you so much for um, thank you.